The universe, a vast and largely empty canvas filled with asteroids, planets, stars, and everything in between. But what exactly is it that fills this space that is in between the stars? Only an estimated 4% of matter in the universe is visible, with most of the mass coming from the elusive dark matter and energy. Gas clouds account for 10 to 15% of this visible matter in the universe and are known as an interstellar medium, as they are found in the space between stars. The clouds consist of around 1% dust, and the rest gas, about 90% hydrogen and 9% helium, with traces of other elements. It is from these clouds that the stars are born. The clouds are usually in equilibrium, with gravitational force towards the center balancing with the outwards kinetic force. However, sometimes the balance is disturbed when a cloud becomes too large. The gravitational force becomes too strong and the cloud collapses inward. As the cloud collapses, it fragments into smaller pieces, at around 10 to 50 solar masses. These fragments of gas cloud begin to condense into small, rotating spheres. These will soon become protostars. For a star the size of our Sun, this phase lasts about 10 million years. Eventually, the temperature in the protostar will become great enough that hydrogen will begin to fuse into helium, and the protostar becomes a star. The larger the original gas cloud, the larger the star will be. Not all stars are similar to our Sun. The universe contains many different types of stars. The Hertzsprung-Russell diagram displays these types of stars, showing average temperatures and brightness. These stars appear to fall into distinct groups. The distinct band across the middle shows the main sequence stars, which are the most common types of star in the universe. Our Sun belongs to this group. As well as this, there are giants and supergiants in the upper right, which are very large and bright but not as hot as other stars. In the bottom left are the subdwarf stars, which are small and dim, yet very hot stars. All the main sequence stars are actually dwarf stars. There are 6 types of dwarf stars: red, white, yellow, blue, black, and brown. Although blue and black dwarfs are only theoretical, yellow dwarfs are stars with masses similar to the mass of our own star, the Sun, making it a yellow dwarf itself. Yellow dwarfs will fuse hydrogen for about 10 billion years, before expanding to a red giant and then shedding its outer layer and contracting into a white dwarf. White dwarfs are what stars like our own Sun become after they have used up their hydrogen supply. Red dwarfs are the most common star found in the Milky Way, and the Sun's closest neighbor, Proxima Centauri, is a red dwarf. These have a small mass, much less than our Sun. Brown dwarfs are stars not massive enough to fuse hydrogen and helium but can fuse deuterium. These blue dwarfs and black dwarfs are only hypothesized stars, as the universe is currently not old enough to have produced these stars. Blue dwarfs come after red dwarfs have used up their hydrogen supply, and black dwarfs come after white dwarfs once they have cooled sufficiently so that they no longer emit any light. Giants are stars which are much larger and much brighter than main sequence stars, and are cooler than the star they formed from. Stars similar to the size of our Sun will become red giants. A main sequence star will become a giant after all the hydrogen within its core has been depleted. Once this happens, there is no longer energy keeping the star from collapsing, so gravity takes over and pulls the star into itself. At this stage, the pressure and temperature greatly increases so that helium atoms can begin to combine into carbon atoms. This energy pushes the outermost layers of the star out, and it becomes larger than its original size. The cooler temperature gives the star its red color. A star much more massive than the Sun will become a red supergiant, which will eventually become either a neutron star or a black hole depending on its mass. Stars can also become blue or yellow giants. Blue giants will eventually become red giants and follow the same process, and yellow giants only formed from very massive stars and are very cool. At the end of the red giant's life, the core becomes a white dwarf and the outer shell a planetary nebula. This is a misnomer, as this phenomena has nothing to do with either planets or nebulae. In the grand scheme of things, this stage of the star is very short, lasting only a few tens of thousands of years. A planetary nebula is formed when solar winds dissipate the outer atmosphere of the red giant. Radiation from the red giant's core ionizes these lost outer layers. This energizes the gas and causes it to glow, appearing as a brightly colored nebula. Supernovae occur at the end of a massive star's lifetime, so a star much bigger than our Sun is required. These stars are able to continue fusing elements beyond hydrogen and helium because of their size, and eventually, they form an iron core. At this point, the star can no longer get energy from fusion, and the core collapses in on itself. The rest of the star also begins collapsing before it explodes. This is the supernova, or a stellar explosion. The supernova produces an extremely luminous burst of radiation which pushes the outer layers of the star into space at velocities of up to 30,000 kilometers per second. The light from the supernova can be bright enough to briefly outshine the entire galaxy that is part of. The shock wave created from the supernova sweeps up an expanding shell of gas, known as a supernova remnant. What is left in the center of the explosion is a very dense neutron star, or a black hole. Another way that a supernova can occur is when we have a binary star system. A white dwarf orbits another star, stealing matter from it until it has absorbed too much matter, which causes the dwarf to explode in a supernova. Neutron stars are the tiniest and densest stars in the universe. Although having a mass several times the size of our Sun, their radius is only about 10 kilometers. Stars which have a mass too great to become a white dwarf yet too small to eventually end up as a black hole will become a neutron star when they undergo a gravitational collapse. As the name suggests, these stars are composed mostly of neutrons and are very hot. Some neutron stars, such as this one, rotate very rapidly and emit beams of electromagnetic radiation. These are known as pulsars. A black hole is a region of space-time which prevents anything, including light, from escaping. This means it is impossible to see a black hole. Around a black hole is something called an event horizon which marks the point of no return. If you were to pass this point, you would not be able to return. Anything that hits this horizon is absorbed, and nothing is reflected. Black holes form when a massive star collapses at the end of its life cycle, and it will continue to grow by absorbing mass from its surroundings. By absorbing other stars and merging with other black holes, supermassive black holes of millions of solar masses may form. Supermassive black holes exist at the center of most galaxies. The core of the Milky Way contains a supermassive black hole of about 4.3 million solar masses. The presence of a black hole can be inferred by observing its interaction with other matter. So, stars are where all the elements were made originally, and without stars, the Earth would not have been formed, life would not exist. Stars are where we came from, which is one of the reasons it's so important to have an understanding of them and to keep studying them.